Or I'll let you watch this one because this is the one we did together. Okay, so these are a series of 4 Venn diagrams. Venn diagrams, you may have seen these in your education history. This is something you learn about Venn diagrams very early in education. If you didn't learn, you're going to learn them now. The idea is that this rectangle it is a representation of S, the sample space, all possible outcomes. Like we have taken phenomena that is not neat at all, is it? All so all possible outcomes are here, and it depends on how you define it. All possible outcomes in this rectangle include event A and event B, 2 possible outcomes. These events are known as complementary. So you may have heard these terms before. The reason I do this overview without teaching you things in advance is because you've probably seen these things before. You've heard this terminology before. And I want to put us all on the level playing field of understanding of the terminology and clarify any misunderstanding that you might have brought with you. So complementary, what does complementary mean? Looking at the image. How would you describe complementary? And then give me an example. No comments? Am I going to call names? You can get it wrong. It's okay. All right, I will give you the answer. Complementary events are events that complete the space. So they fill the space. A and B fill the space. They are the only possible outcomes. And to call them complementary, there's only 2. And when A doesn't happen, we know B happened. So this could be, we could define A as it rained outside. And what's the complementary event to rain outside?
It was sunny.
Okay, we'll be more, because it can rain and sunshine at the same time in Puerto Rico. So we'll just say no rain. Very simple. But I see what you're saying. Okay, so rain or no rain? Only I've divided all states of the world into 2 possible outcomes. It's either rain or no rain. And that's, other things can happen, but that's not what I'm caring about here. I'm trying to define the rain phenomena versus no rain. So let's say event A has a 30% chance. I could have come to this by collecting data over a long period of time and making a histogram of, well, I guess if it's rain or no rain, I'm not going to have a histogram. If I have rain or no rain, I'm basically going to just calculate the number of times there's rain and the number of times there's no rain and do it enough times to believe that I have a good representation of what's going to happen in the future. Maybe I'll get some other information about climate change or something like that and help make a prediction. Though here's a number, 30%. So if the chance of rain is 30%, what's the chance of no rain?
%70.
That's right. It's going to be 70% because why? So what I'm appealing to here is your intuition. You know, we learned with the normal distribution, when we looked at the relative frequency histogram, you know, that we would say that that's 100% of possible outcomes. This is another way of seeing all possible outcomes. And the total in S should be 100%. So if PA is 30%, PB should be 1 minus
70%.
PA or 70%. That's right. So P minus A. So we saw that with the normal distribution as well. We had to use 1 minus to figure out the other side of the distribution. If I'm going to go left, if I'm going to go right, I use 1 minus if I know the left. If I want the left, but I know the right, I use 1 minus the right to get the left. All right, so we already know that rule, the complement rule. We're just putting a label on it. Okay, so now that we know that, find me the different compound events. So these are compound events. I'm going to combine A and B, the only possible outcomes. And this means A and B. This one is A or B, and this one is not A or B. Now, how does that apply to this drawing? What would A and B, what does that mean? So we can also write it like this. I wrote it wrong. Sorry. I wrote that wrong. My apologies. Probably A and B. I don't know what I was thinking. So this is the intersection, is the way you refer to that, of A and B. In this Venn diagram, do A and B ever coincide? Can you both have both rain and no rain at the same time?
No.
No. So for complementary events, it doesn't even matter if I know the value of A or the value of B. I know that complementary events will never intersect. Always true for complementary events. So these are the results for complementary events. This, I don't know, in the notes, I think I add the numbers in the presentation, but I have the numbers written here for the overview document. All right, so what about A or B? A or B refers to A. So you can be in event A or you can be in event B. That's different than A and B, which means it has to be both at the same time. A or B is either it's raining or it's not, which kind of is silly for complementary events because we know it's going to be one or the other. So what is the probability of rain or no rain? Sergio?
I don't know the answer.
It's right here. The only possible outcomes are A or B. So if you're going to be served either rice or beans, and those are the only possibilities, what's the chance that you eat rice or you eat beans?
Well, I don't know, it should be 50-50 then.
No. So I'm not saying one or the other. I'm saying that either one of these can happen. This or this can happen. When events are separated like that, you add the probabilities together. So in this case, whatever they are, dollars, whatever they are, it's 100%. It doesn't really mean that I need to know 70 and 30. Complementary events will always have a 100% chance of happening. I'm not asking you what's the chance of A. I'm not asking you what's the chance of B. I'm asking you what's the chance of one of them. If one of them has to happen, then there's 100% chance that one or the other happens. That's the interpretation. I hope that helps. So basically, A or B means the whole thing. So if I'm here, if I fall here, the chance, no, it's not gonna be a good way to explain it because it looks like I'm an A. Anyway, let's see if in the other examples you'll understand better. All right, are there any other possible outcomes in this sample space? Given how to define A and B, the only possible events. By definition, there are no other events possible. Okay, there's either A or there's B. So this is what this is asking. This is asking, is there anything else that are not A and B? This is like anything else. In this example, there is not. There's only A, B, and nothing else. It's 0. To break it down a little bit more, before I give you that answer, the way that you deal with a not event is a complementary event. Okay, so we can write A, C, or not A. If events are complementary, AC is equal to B and not A is equal to B. Put it at the top. So whenever you see a complementary event, you can calculate it like that, just like I did here. So this is probability of B because B is not A, which is 1 minus probability of A. So just like B is not A, 1 minus probability of A, then not A or B is 1 minus probability of A or B. But what was A or B? What's the probability of A or B?
100%.
Right from here, 100%. So that means that probability of not A or B is 0. All right, any questions about complementary events? It doesn't really matter to know the probabilities, although I've given it here and I'm going to use those same numbers. I'm going to use similar numbers once I present them here. It doesn't really matter. To calculate this, I didn't need to know A's probability. It didn't go into my calculations. I just know that these add to 100 and this, there's nothing else basically. There's nothing other than A or B. Okay, let's go to the next one. The next one is a depiction of two events that are disjoint. So it describes what disjoint means. What can you tell me about disjoint? Events. Well, how are disjoint events different from complementary events?
They are not related.
The word would be that they do not intersect. But you're right. They do not intersect. They do not relate or intersect. It's okay. It's a good word, but there's a better word. I mean, there's a word they use to explain that, and intersect. So they do not overlap or intersect. So disjoint events they do not overlap nor intersect. What's something else you can tell me? What's something else you can tell me about that compares to the complementary ones? A and B in complementary events fill the space. Do A and B fill the space in disjoint events? No. So in other words, there's something else over here. What do we call this something else? We have a symbol for it. The whole outside space is not A or B. There's other things going on, but it has nothing, it's not related to A or B, or it's not A and it's not B. Okay, so there's actually like 3 things possible. A, B, or not A or B. How many things are possible in complementary events? Only 2. Okay. So now I'm going to give you the probability of A, the probability of a B, and I'm going to ask you to think about computing the three compound events that I computed above, A and B, A or B, and not A or B. Let's see what you can do without me. So this is, again, an exercise to appeal to your intuition and correct any misunderstandings in your intuition. Okay, what did you get? Or what do you think? Or where are you stuck? What's the probability of A and B? Do A and B ever intersect? No.
No.
So even if I knew the numbers, doesn't matter, this will be 0. So disjoint events, in that way, they're the same to complementary. The intersection doesn't exist. Now, A or B is not straightforward because they don't fill the space and make 100%. But I gave you the values. Now you have to figure out what to do with those values. What's the probability of A happening or B happening? So this could be, let's say, we can talk about, okay, so I'm gonna lean on an example later because I used to teach nurses statistics and social workers statistics. And most of those people were female, not to stereotype, but they were pretty much always female. So, and they also were not, they were struggling with mathematics. So I had to use something, an example that they could, I guess, relate to. So I use an example of the hair salon or a salon, beauty salon. So in this salon, in this space, S for salon if you want, there are procedures that you can get, but on one day you can only get one procedure at a time. And they do hair coloring, manicures, or they do haircuts. That's all they do. Hair coloring, manicures, or haircuts, but you can only do one of them on a certain day. So this represents a sample space on a certain day. And the chance that someone is here was found to be 30%. And we're going to talk, after we finish this, we'll go into talking about what does that mean a little more specifically. So this one is 30%. This is the hair color. The manicure is 40%. And the cut is what? That's what we're thinking about here. So let's just talk about the hair coloring or the manicure. What's the chance of a person either having a haircut or a manicure? The way you figure that out, if they're disjoint events, is you just add them. That's the rule. So what do you get? 70%. And then we said haircut is outside. Hey, don't be mad at me, but I'm going to change the order of the numbers just so it corresponds to what I did before. So it's going to be 30%. But I said that was hair color. A was hair color. So this is going to be 40%. Now I have to check again. Hold on. Hold on. So I said A is manicure and B. Okay, so this is going to be manicure. This is hair color. And this is haircut. So you can add them like that or as decimals, it doesn't matter. All right, and the last question, what is the chance that it's not that someone is not getting a manicure or a hair color? In other words, they're getting their haircut.
30%.
How much?
The 30%.
30%. So it's going to be 1 minus probability or A or B, which we already have, which is 1 minus 0.7, which is 0.3 or 30%. Okay, so this is pretty easy. But we have to have a good foundation of our understanding. Everything's been pretty straightforward so far. Tell me about the relationship between complementary and disjoint events now. Can disjoint events be considered complementary? So let's go back to the complementary for a second. A and B are the only possible events in a complementary space. Now I'm going to ask again. Can disjoint events be complementary?
No.
No. Okay. No, because we're not filling the whole space. And if they were complementary, A and B would have to be 0, A or B has to be 100, and not A or B has to be 0. That's not even just one example here proves that wrong. Okay, it's not complementary because I just used one example and this is not 100 and this is not 0. So, and it's all because they don't fill the space. There's something else that's possible. All right, so can complementary events be considered disjoint? So what is disjoint? The disjoint part is they do not overlap nor intersect. So it's a weaker This is like a weaker requirement than complementary. Complementary forces it to be the only two events. So disjoint events are considered, complementary events are considered disjoint, but they're more than disjoint. They're also complementary, okay? So because they don't intersect, we'll say complementary events are disjoint, but not the other way around. All right. Okay, so we have exhausted all the possible things I could say about these two things. All right, so now we have the next relationship between events. And notice we're just doing this two at a time. And there's actually 5 ways you can see 2 events at a time. So we're going to talk about all the 5 ways. There's only 4 on this, on the overview. You can have more than 2 events. You can have a lot of events, but I'm just teaching you the theory, starting with the basic 2 events. Okay, let's move to overlapping events. Here's a depiction of 2 overlapping events. So I'm also going to use the same numbers, but this image. So now we have some different possibilities. We have that a person can have, well, we have that event A can happen, event B can happen, and what's this? What will we call this? That is the intersecting piece, or A and B. And I've actually given to you what it is. Otherwise, you wouldn't know what it is just from these numbers. In addition, you have, well, you have A or B, which would be all of this. But we have to be careful. We don't want to count this twice. So we need to deal with the fact that this overlaps. And then we have the stuff outside. So those are all the possible compound events. Event A, which is here. Event B, which is here. Event A and B, which is here. And outside here, we have not A or B. Out here. So let's go back to the salon example. I hope you like it. This is the chance of having a manicure. This is the chance of having your hair colored. And there are some people that get both manicure and hair color. But the way that this salon works, if you get your hair cut, you can't get any of these other products or services. Okay. So not A or B is out here, just like it was up here. So let's try and calculate with what I've given you. Please calculate A and B, A or B, and not A or B. How did you do? So what would be A and B? I already gave it to you, so you just put that there. It's given. If I don't give it to you, there's nothing special to tell me how to get that intersecting part. Okay? So it's 10%. What about A or B? How do I figure that out? I take the probability of A. Let me make this bigger. I add the probability of B, but there's a problem because if I take this and then I add this, I double counted this. So I need to subtract that off. Which I already have the number. So you notice if I didn't give you the number, you couldn't calculate this either. Okay, I'm gonna grab some water. I'll be right back. You guys finish that. Okay. So what else? What is not A or B? 1 minus probability A or B, or in other words, 1 minus 0.6, which is 0.4 or 40%. Any questions? So this person gets both manicure and hair color, person in here, a person that's, if you want to know the chance of a person getting manicure or hair color or both, it's 60%. And someone who's just getting a haircut or not a manicure or a hair color is 40%. So just to specify some points here, this is known as the general addition rule. Let me put it in a red box. And this one is known as the addition rule for disjoint events. Okay. All right, so all that was probably straightforward and clear, and I maybe spent too much time on it. It was all to bring us to the third one. The last one, sorry, the fourth one. Here is an example of what is called independent events. A and B are independent here, provides information on what the intersecting probability is. The event that of A and B occurring at the same time and the chance of it occurring can be computed now because we've been told that A and B are independent. What does independence mean? Independence refers to the fact that knowing that I'm in event A doesn't affect knowing the probability, or doesn't affect the probability of B happening. So an example of independent events would be consecutively flipping a coin. From one flip to the next flip, the chance of the, okay, so the chance of seeing, let's say, let's write it down a little bit here. On a coin flip, the possible outcomes are head or tails. If I know that on one flip I got a head, what's the chance of a head on the next flip? So if I flip a coin the chance of seeing a head is how much?
%50.
50%. And we're going to talk more about that when I finish this. But yeah, it's a 50% chance. One way to look at it is there's only two possibilities. They're equally likely, so each has 50% chance. After I flip the coin once and I see I have a head, the chance of seeing a head on the second try is how much?
50%.
50%. It doesn't matter what happened before. You again face the same odds. All right. That's independence. So back to this example. If we're told that this hair salon has clients who choose between services in an independent way, services of manicure and hair color in an independent way, what does it mean? It means if you know someone had a manicure, just like the coin flip, it doesn't affect the chance that they got their hair colored. So A is 30%, B is 40%. And essentially it means if I'm here, the chance that I'm here is exactly the same as, well, I got to show you, I think. Okay, let me take a little moment to explain what this event means. Okay, let me take some time to do that. Let me clean this first. This is the rule or the way you would calculate the probability of A and B if you weren't given the number or if I didn't tell you they were independent. This is the general way you would do it. I'm going to erase this, but this is just a multiplication. I just want to show you in case people don't understand what I'm doing. Oops. If you don't understand what I'm doing. So this is multiplied. So what does this mean? This is the probability of A, and this says that I have to multiply it by the probability of B given A. That line there means that like A already happened. Okay, so this is what A and B is. Now to be able to calculate this, you need to know both of those things. You need to know what the probability of A is, and you need to know what the probability of B given A is. If A and B are independent, I know what that is. So we'll go back to the definition of independence. Knowing that A happens, the probability of B does not change. So if they are independent, then this is just equal to probability of B. That is a way of explaining what independence is. So what's the implication of that? It means that to calculate this in here, all I have to do is multiply A probability. Let me write it smaller. I'm just going to write them next to each other. I don't want you to think X is another variable. Okay. All right. So given that information, the fact that they're independent, it still looks like overlapping. But in calculating this, you can calculate it automatically without knowing this extra term, because you know this extra term reduces to just being the probability of B because of independence. It doesn't matter if A happened, the chance that B happens doesn't change, just like the coin flips. So what is probability of A and B? It's just probability of A times probability of B, which is 0.3 times 0.4, which is a little bit bigger, 0.12. Let me go back just to finish this off, because this could also be written another way. I could have focused on B. And then the probability of A and B would be probability of B times the probability of A happening given B. And because they're independent, if B happens, the chance of A happening doesn't change. And you see, either way I do it, I get the same result. It's A times B. Okay, so the rule is it's a multiplication rule that you just times the probabilities in the case that what? A and B are independent. Okay, if A and B are independent, you can multiply the probabilities to find their intersection. If A and B are disjoint, you add probabilities to find their union. So that's kind of two different things you need to tease apart, and the fact what is independence. So those are the main things to get out of this. Independent events overlap. Independent events are not disjoint. The overlapping part is computed as A times B if the events are independent. If they're overlapping, but they're not necessarily independent, you have to rely on other information to know what the overlapping piece, the chance of the overlapping piece is. Okay, what's the probability of A or B? What did you get? What did you get? What happened? I drew on here. Oh, somebody else drew on there?
Sí, yo.
Did you draw on there?
Sí, es que no sé de dónde sale eso.
Oh, that's this is the, can you see my cursor?
Yes.
This is the definition of independent. Knowing A does not change the probability of B. That's a way to write it.
Pero no es una fórmula.
No, no, es un
la fórmula para
concepto, es
hallar
un
no es esta.
concepto, es un concepto. No,
Okay.
okay.
Ok.
El fórmula nuevo es eso.
Es solamente A por times B.
This is, okay, so let's go through what we learned. These are the new thing I'm teaching you, right? These are the formulas.
Ajá.
That A and B should be the probability of A times the probability of B given A. This to here, this becomes this if A and B are independent. That's a concept.
Okay.
And the fact that I give you this one is also new.
Okay.
Everything in red are the new formulas. So, well, I put it in words here. Addition rule for disjoint events, I could put red. I'll put red around there instead, maybe.
Okay.
Okay, so those are all like formulas that we have to know now.
Okay, gracias.
Good. Okay, so let's get number 2. How do we calculate this? We're going to use this formula here because they overlap, right? So we have to use this one here. So it's going to be A plus B minus A and B. So A is 0.3 plus 0.4 minus 0.12. And the answer? So independent events doesn't change this formula. This is the same formula. The only thing that changes, we have an extra formula here because of this independence. So the answer is 0.58, right? 58%. So the chance of a manicure or a hair color is 58%. And what's the chance of a haircut? A haircut is out here. I'll be right back. Okay, what do you get for not A or B?
One minus A or B. So it will be 1 minus 58.
It's 42%. I'm going to move it over because it looks messy there. Okay. All right. Any questions? So that is an overview of the way two events can be related. They can be complementary, where they fill the whole space and there's only two possible. They can be disjoint, where they never overlap, but there's other events possible. I could just call this not manicure or hair color and leave it uncertain, but just call it not A or B. I don't have to give it a name, but I just did for an example. They could be overlapping. In the case that they're overlapping, I don't necessarily know this intersection piece. I would have to calculate it. I would need information. I would need information on the event of B happening. If you knew A happened already, the probability of B happening if you knew A happened already, or the probability of A happening if you knew B happened already. If you don't have that, if someone doesn't give that to you, you'd have to know this. Or if they tell you the events are independent, then you can calculate by just multiplying. So we reviewed many of the rules of probability, and I take some time and go through them step by step in the notes. What I'm going to do now is just show you the fifth way that they relate. And that is in the notes. I'm going to stop sharing that. Here's a fifth way that they can relate. I go through the notes and I explain using a particular example about flipping 4 coins and all the possible outcomes. You can review that, okay? So I want you to review the videos I've put up. But I want to emphasize just using this example here, if you can depict these probabilities in the sample space. So draw these in the sample space, and then we'll ask the same question. What's the probability of A and B, A or B, and not A or B? Okay, so draw those in the space. And when you review the notes, you'll go through and see what they all mean. I mean, what the events A and B have to do with flipping 4 coins, as explained here. So how would you depict? Just looking at those numbers, are A and B complementary, disjoint, overlapping, or independent? What would you say their relationship is? Can you tell by the numbers? Here are the possible outcomes of flipping 4 coins to help you understand better. I define compound event A as observing 2 tails in 4 flips of a coin. There's 6 ways to see 2 tails in 4 flips. You can have a head, a tail, a tail. You can have a head, a tail, a head, a tail. You can have, okay, so there's 6 different orders or permutations, rearrangements of the heads and the tails. Compound event B is observing less than 3 tails in 4 flips of a coin. So these are the ways you can see either no tails, 1 tail, or 2 tails. What do you notice about A and B? What's the relationship? Any revelations? Do you see anything special there? I noticed that A and B share outcomes. In fact, A is completely inside of B. So they don't exactly overlap. B includes A. So this is the fifth way that the events can relate or, yeah, coincide. So knowing that, how many of you understood that or saw that? No one? What I want you to do now is calculate, like we did with the other exercises. I want you to calculate the probability of A and B, the probability of A or B, and the probability of not A or B. Okay, so what do you get? What is the probability of A and B, them happening at the same time? Where do they happen at the same time? Only here. If you're here, you're both in A and in B. So it turns out when one is contained, we'll refer to this as a contained relationship. A contained in B. Then the probability of A and B is just the probability of A, which is 0.375. What about probability of A or B? To be in A or B is just to be in B, which is 0.6875. And the probability of not A or B is the outside, which is equal to 1 minus probability of A or B, which is 1 minus that over there, 0.6875, which is 0. Like that. Or it's a 3, sorry. Any questions? Any question? Was this useful? How are you feeling? All I'm doing is reviewing 2 events and the possible ways they can be related. In the process, I'm clarifying intuition you have from probability and try to catch where you might have some gaps or misunderstandings. Okay, what I'm going to do next, I'm just going to talk a little bit more about independent events. And then I'm going to go. I'm going to let you guys go and work with this. What I'll do for the test is I will do it like last time. I'll put a bunch of questions. Just make sure you do enough of probability that you understand that you can answer some questions, okay? You don't have to do them all. Just pick the ones you're good at, but I will leave it to you to study probability. Everything's there for you. The videos are there. And there's a lot of stuff because it's a lot of stuff. Once you get to Bayes' rule will not be on the test. So if you want, you can skip it. I think it's important, again, for completeness. I'll put it there, and I encourage you to listen to my explanation or my videos. Bayes' rule. Bayes' rule starts at, so I'll say optional. All of this is good. So Bayes' rule starts here on page 33 and goes through page 35. It's not that many pages either. Pages or PP. Optional, but I also have quizzes with Bayes' rule in it. The quizzes online have Bayes' rule, so you should review them to do the quizzes when you get to doing the quizzes at whatever point. After Bayes' rule, so it's broken down like this. First, I do the probability rules. Then I review the types of probability distributions you will see in this course. Then I do Bayes' rule for a very short time. So this is all just review of probability rules. And then I do this. I spend the rest of the unit talking about rules for means and variances of random variables. This is not hard. It just seems tedious, actually. I don't expect you to derive the formulas. I just expect you to be able to apply them. I provide you from page 42 to '48. So from page 42 to 48, I have a number of examples. Not for, well, this one 42. Okay, so from 42, I apply the theory of the rules. So, I have it all in the videos. I'll just encourage you guys to watch those. I'm just going to be repeating myself otherwise, and you guys might be too tired to catch it anyways. So that's what it is. It starts with the probability rules. Then I teach you about probability distributions, and I simplify the kind of distributions we're going to see, and they're very few in this course. Then I do Bayes' rule. And then I do the rules of means and variances. And for the final exam, you're going to have to know this material. I'm going to ask you at least one of these problems, something similar to, so basically you have to study them to understand them for the final exam. It's not going to be too heavy for the midterm, but there will be problems, but you can choose which ones you want to do. All right, so let's go back here where I want to talk about what probability is, okay? So back to my hair salon or my beauty salon example. In your notes, I wrote case 3, but it's case 4 in the diagram we discussed that you have in A and B are independent events. And I want to take a moment to explain what I mean when I talk about probability. Probability is long run relative frequency. It means that I need to see enough occurrences and enough changes from phenomena to phenomena. I need to see enough occurrences to be able to generalize. So let's say 10,000 clients of the beauty salon, which is, let's say it's all for women. It's very female. So 10,000 clients of the beauty salon is enough time to see the long run relative frequency. Out of those 10,000 women, 30% of them have a manicure. Remember, 30% was probability of A, and we called that manicure. So that means 3,000 women have a manicure, if 10,000 is enough to realize the 30% probability. If manicure and hair color are independent, then because of independence and because the hair color probability is 40%, it means that 40% of the 30% of women also have their hair colored. The probability doesn't change. That's what independence implies. So in other words, in the subset of women who've had a manicure, 40% of them have their hair colored too. How do I interpret of? In English, when you say the word of, you mean to multiply. I want 40% of the 3,000. In other words, I write 40% of 3,000. So 1,200 women have both. If I didn't do it this way and I just did it from the beginning and I ask, what's the probability of A and B? You would just calculate A times B because I told you they're independent. And that would be 0.3, 0.4, 0.12. You see? And then if you took the 10,000 of the women and you times by 0.12, what do you get? So mathematically, you get the 1,200, but I'm trying to show you step by step what it means to be independent. It means that in the subset of women with a manicure, it doesn't matter they had a manicure. The chance that they have their hair colored too doesn't change. It's also 40%, just like it is of the general population. Let's do it another way. Let's do it the other way. Let's start with the women with their hair color. So 40% of women have their hair colored. That's 4,000 women. Of these 4,000 women, because of independence, 30% of them also have a manicure because the probability was a 30% overall for a manicure. 4,000. So of the 4,000, 4,000 times 30% is 1,200. So every way we get our 1,200 women have both. Now, is that normal? is it normal? Is it expected that a woman, the chance of a manicure and hair color are independent? If you're going to a salon, I'd say it pretty much depends on the price. If a manicure costs $150, like there's some crazy places they charge a lot, and your hair color costs $250, just getting one of these might be too expensive. You're not going to get the other one. So it's not necessarily true that they're independent. It's probably more true in a case like this that they aren't, that they're dependent. Okay, that once you have your hair color, you're not going to get a manicure, or the chance of getting a manicure changes. So if it started like 30% and 40%, the chance of a manicure the chance of A given B is not equal to 30%. Maybe it goes down. Maybe it goes to 10%. Because people are out of the market. They don't want to spend any more money. Okay. So this is an example of dependence. What will that look like? Well, there's still overlapping events, but calculating that A and B is not that easy. It's not just A times B. You need to know this number. You need to find this number to make the calculation. Okay. Any questions for me? So there's like 5 hours of videos. Oh, there's more. There's more there. But we've done a lot of the first one. Because I always start with the let me see. Just want to check. I'm still doing correlation here. Okay, so yeah, the first video has just what I'm talking about events being disjoint and blah, blah, blah. The second one gets into it. And then I go over all the notes. I do everything. So do your best reviewing the videos. You have about 4 or 5 hours on there to review. If you need me, contact me for anything. If you're stuck, if you want me to do, just explain something again. But there's enough exercises in here and explanation that I think like this is a really good one here. I really like this, and it should be in the video too, where I go through the assignment. So I spend time on the assignment. So can we do that? We'll let you go and then you guys work and let me know if you need any help. If you want, we can even meet Wednesday night for questions. Do you have class on Wednesday? Okay, so if you want, we can meet on Wednesday night. You guys can ask me to review something or answer any questions. Let's set that up tentative. You don't have to come. I'll send an email to let you, well, whatever. On Wednesday night at 6, let me make sure I'm promising without checking. Let me check here what I have. So Wednesday night at 6, I will just come on, and if you want to come in Zoom, you can come in. Just put it on your schedule. Okay? Put it on your schedule. I'll be here at 6. And if you don't come at 6, but you want to talk at 7 or 8, just email me to make arrangements. Okay? So I'll send you an email just to remind you. I'll send it today because I don't know. I probably should send it next week, but I don't want to forget. I might forget. But I'll send it today and you can just put it on your calendar. Okay? Do you have any questions for me right now? If you want to know your test result, just email me. I can tell you your result. But you'll get it next week. I'll give it to you. It's like it's hard to share the results when you don't have the paper. Like you need to see what you did. I had a lot of trouble marking. I made a mess because I had a clave. I was using like the wrong clave, so I made a mess of well, not a mess, but I have a lot of scratching out of my red. So what you can do when you get your exam is go through, when you go home that night, go through the clave that I put on and make sure I graded it properly, because it's possible that I did something wrong. I did check it like so many times, but okay. Questions for me? No? You're good? You're gonna have a good night? We're gonna see you on Wednesday or before. Let me know, okay? Buenas noches.
Buenas noches.
Buenas
Buenas noches.
noches.
Bye.